Hey, welcome back to Computer Science Theory. This is COMS W3261, offered Summer B 2021 at Columbia University, and this is Lecture 7, Part 2, where we'll show how to convert a pushdown automaton into a context-free grammar, and we'll also talk about the pumping lemma for context-free languages. So in the previous part of this video, we showed if you had a context-free grammar, you could build a pushdown automaton that recognized the same language. And the intuition was that we went from a start state, we pushed something on the stack, that is a $sign to mark the bottom of the stack and a start symbol. And then once we were in this looping state, what we did is we non-deterministically tried to guess a derivation that matched the input string. So we substituted variables and matched terminals with the input string, and we accepted precisely if we found a branch where we could derive the input string, sort of in real time on this pushdown automaton. So that proved that we could go from context-free grammars to pushdown automata. Now we have to show how to go the other way to complete our proof that these two ways of describing languages are equivalent in power. So here's lemma 2. It says, if a pushdown automaton recognizes some language, then that language is context-free. And what I'm going to do here is try to split the difference between doing a proof in full detail and not giving you any intuition at all. So I'll say the full proof is in section 2.2 of CPSR. I'm going to try to spend the next 15 minutes or so giving you a strong intuition for this proof, so you have some idea of how it works. But as usual, when we don't do a full proof, when we just do a sketch, you guys won't be responsible for all the precise details, some of which I will omit. So let's start thinking about how to turn a pushdown automaton into a context-free grammar with a picture of the stack. So here's a picture. Consider some computational path that takes us from state Q1 to state Q2 with an empty stack at the beginning and end. So in other words, we're going to draw a picture of a snapshot of computation. Q1 and Q2 aren't necessarily the start and accept states, but we're just going to imagine some branch that takes us from Q1 to Q2 in some pushdown automaton, and where the stack is empty at the beginning and empty at the end. So here's Q1. Here is Q2. And we'll imagine, there's a bunch of intermediate states in between. This picture is generally true. If we go from Q1 to Q2, we go through some intermediate states, and then we will plot the stack height as we go from Q1 to Q2. So the stack height is at 0 at Q1 and Q2, but in between, maybe we push some stuff onto the stack, maybe we pop some stuff off to the stack. At some point, we might even go back down to 0 again. we might end up with a picture that looks like this. Our stack is growing and shrinking as we push items on and pop items off. Maybe it comes back down to 0 at some point, or maybe it doesn't. So we'll use the following idea. Suppose we have a CFG variable, A, Q1, Q2, that generates all strings that take us from Q1 to Q2 with empty stacks. Then any particular string can be subdivided into paths between intermediate states. So in particular, if we've got some variable A, Q1, Q2 in our context-free grammar, and it generates a string S that takes us from Q1 to Q2, then in the picture above, S is generated by A, Q1, QR, concatenated with A, QR, Q2, where QR is this intermediate point where our stack went to 0. Now, we didn't assume, we may not have any such intermediate point, but the idea behind our proof is going to work like this. We're going to have variables in our context-free grammar that generate strings to take us between states with nothing on the stack before and afterward. Then we're going to create rules that recursively decompose these variables into smaller and smaller pieces, and finally ground out into terminal strings. So that's our idea. Let's sketch how the proof is going to work. So given a pushdown automaton, P, we'd like to create a CFG G that recognizes the same language. Step 1 will be to simplify P so that several assumptions hold. So what I'm doing here is I'm saying we're given a generic pushdown automaton, and we'd like to create a context-free grammar that recognizes the same language. So I'm going to show some generic simplifications I can make to my automaton that'll be convenient, that'll let me assume certain nice things. So in particular, my first condition will be that there is exactly one accept state. Q accept. And to do this, add epsilon edges from the old except states. So essentially I'm saying our PDA might have many except states. We're going to turn our old except states into regular states and add one new except state, sort of like what we did in the proof for the GNFA. 2, we're going to assume the stack is empty when we accept. So although we've seen this a lot, this is not a strict requirement for PDAs. We're welcome to have things on the stack as long as we finished reading the input string when we accept. However, we can make sure this condition always holds by adding edges that look like don't read any input and pop every symbol off the stack to Q accept for all characters in the stack alphabet. So what this is going to do is make sure some branch of computation, once it reaches Q accept, if the input is done and there's things on the stack, we'll just pop all the input off the stack. And our third condition will say all transitions either push or pop, but not both. So at the moment, in a standard PDA, we allow transitions that don't push or pop anything, and we allow transitions that both push something and pop something in one single transition. So to do this, we'll convert transitions that do both into 2 separate transitions. With a new state in between. So in other words, if we have some transition that pushes A and pops B, we'll just split it into 2 transitions with a new special intermediate state. First transition will push A, second transition will pop B. We'll convert transitions that do neither by creating 2 new separate transitions. That push and pop a meaningless symbol. So for instance, if I want to just read in an input string without pushing or popping anything, I'll create 2 separate transitions. I'll push something meaningless random onto the stack and pop it off again. And that'll ensure that all of my transitions push or pop something, even though I've effectively done nothing. So I'm not going to go into more detail, but I want you to believe me that it's possible to ensure that any generic pushdown automaton P satisfies each of these 3 conditions, and that you could do this by following the purple instructions. So again, the precise constructions here are in section 2.2. But the main thing is just we can simplify any PDA to be nice, to have some nice properties. And then we'll assume our PDA has these properties and that we can build a context-free grammar from it. So now, consider any accepting computational path from QStart, that is our start state, to QAccept. Remember now we're assuming that we have exactly one accept state in our pushdown automaton. And we'll say this path corresponds to some string s. So we will create a grammar G with a new variable a sub QStart QAccept designed to derive every string that takes us from QStart to QAccept with an empty stack at the end. So this is all accepting strings. So if we had some nice variable a sub QStart QAccept with this property, in fact, I think I'm going to change it from QStart just to Q0 because it'll mean less writing. So from Q0 to QAccept. Because we've assumed our pushdown automaton has these three properties, there's exactly one accept and the stack is empty when we accept. If we derive every string that takes us from Q0 to QAccept with an empty stack at the end, well, that's every string that's made us accept. So in other words, if we can ensure this condition holds, then we have a context-free grammar that will accept all the strings recognized by our pushdown automaton. So I claim that if we consider any one string s that takes us from Q0 to QAccept, we have two cases. In case one, if we draw our picture again, where this is stack height, then at every step from Q0 to QAccept, by assumption, we're pushing or popping some symbol, we're moving up and down, and at least one place that we'll call QR, we have an empty stack. So case one, stack empty at some intermediate point. So we'll create the rule a sub Q0 QAccept goes to a Q0 QR a QR QAccept. And we'll say these variables will generate all strings between their states with an ending empty stack. So essentially, I've found a recursive case here. I've said, if my string takes me from Q0 to QAccept, that means I want it to be generated by this variable that should generate all the strings that take me from Q0 to QAccept with an empty stack at the end. Then It's also generated by the concatenated variables a, q0, qr. That'll generate some string that takes me, or all the strings that take me from q0 to qr with an empty stack, and qr, q accept. That'll generate all the strings that take me from qr to q accept with an empty stack. So that's case one. And what case one has shown me is I can introduce a rule in my grammar that will break down my variables further. Case two is the other case. Suppose I have some string s that takes me from q0 to q accept, where the stack never empties completely. So in this case, we create a rule a q0 q accept equals, we'll call this q1 and q2 equals a, capital A, q1, q2, b, where a and b are the input symbols read on the first and last step. So essentially what I've done here is I've observed that if we go from q0 to q accept and we never pop everything off the stack, in this first step from q0 to q1, we must push something, and that thing will stay on the stack until the last step, where we must pop something. So the computation in between q1 and q2, that's this bit, the computation between q1 and q2 must look like some string that takes us from q1 to q2 with an empty stack at both sides. So I found another way to break down the computation from q0, q accept into smaller pieces. If I do this, my goal is to eventually generate all the strings that take me from q0 to q accept. So if I'm going to shorten my variable, I'm going to go from a q0 q accept to a q1 q2. I'm going to want to add in the terminals on the input string that have moved me from q0 to q1 and q2 to q accept. So that's what a and b are. They're the input symbols I read on the first and last step. They could be the empty string. So here's a claim that I'm going to leave unproved. I claim that these two types of rules allow the variable a, q0, q start, to generate all strings q0 to q accept. We'll also need to add a base case that says if we have some variable looking for the string that takes state q to itself, this generates the empty string. So my claim is essentially that if I want a q0 q accept to be a variable in some grammar that generates all my strings that'll take me from q0 to q accept with empty stacks, then if I put in a bunch of rules that break Q0, QAccept down in this way, this will allow me to recursively do that. So in any case, in any derivation, I use either the first kind of rule or the second kind of rule, case 1 or case 2. And eventually I boil down to very small variables that look like AQQ, at which point they disappear. And I have generated as a residue on both sides precisely the input string that I want. So I'm not going to prove that claim, but hopefully the pictures give you some intuition for why it's true. I will write down what the formal construction looks like. So say we have a pushdown automaton P equals Q, sigma, gamma, delta, Q0, F. We'll construct a grammar G, that is a set of variables, a set of terminal symbols, a set of rules, and a start state as follows. So the variable set will include a PQ for all pairs of states, P and Q in the state set. So this accounts for all the variables we needed to capture case 1 and case 2. And remember, our goal is for APQ to derive all strings that take us along a computational path P to Q with the stack empty at the end. The start symbol will be A, Q0, QAccept. And by our assumptions on the form of the PDA, any string that takes us from Q0 to QAccept, that's precisely a string accepted by our PDA. We've made the assumption that any string that does that will do so with an empty stack at the end without loss of generality. The set of terminal symbols is just the same as the terminal symbols in our pushdown automaton. So the last thing to do is to define the set of rules. So for all pairs, or for all state triplets, P, Q, and R, add the rule APQ takes us to a PR ARQ. So this accounts for case 1. This says if we're considering strings that take us from P to Q with an empty stack at both ends, well, that's certainly true if a string takes us from P to R with empty stacks at both ends, and then from R to Q with empty stacks at both ends. These rules might be barren. They might not generate any productive strings, but that's totally fine. For all state quadruplets, P, Q, R, S, and Q. And for all stack alphabet symbols, alpha. And for all A, B in the input alphabet, we say if we push alpha and move to state R from state P when we see A on the input tape. So this is saying if we're in some state P, we read in an A, and we move to state R and push alpha on the stack. And also, if there's some other state Q, and when we move from state S on reading in B, and pushing alpha off the stack to state Q, we add the rule APQ to A R S B. And this is a lot of symbols floating around, but the picture to keep in mind here is just, suppose we move from state P to state R, and from state S to state Q, doing something like this. We're basically writing down the conditions. Suppose we're in state P, we read in an A, and then we push on alpha. And then suppose we're in state S at the end of some transitions, we read in a B, and we pop off alpha and go to Q. We just want to add this rule, this case 2 rule, APQ to ARSB, where A and B are the input symbols that caused us to make those transitions. And then finally, we'll have our base case rule. So for each P and Q, add the rule APP to the empty string. And that's just so all of our rules ground out. So my claim about this construction is as follows. I claim that APQ generates the string X if and only if X can bring our pushdown automaton P from the state P to the state Q with an empty stack at both ends. And this is a proof by induction. So if we wanted to actually go through this proof, as you can see in CPSR, essentially we start from states that are very close together. We build up from our base case, and we eventually are able to show that it's true for all variables APQ, including AQ0, Q accept. So thus, A Q0, Q accept derives strings that take us from our start state to our accept state with an empty stack at the end. By our original simplifying assumptions, this is the language recognized by P. So remember, we had some simplifying assumptions, one accept state, empty stack at the end. And we made those without loss of generality by essentially observing we could turn any pushdown automaton P into one that satisfied our assumption. So that is our sketch of the second half of this lemma. And we have the following takeaway. Our big high-level message for the day. Lemma 1 told us that we could go from a context-free grammar to a pushdown automaton. Lemma 2 said a pushdown automaton could be turned into an equivalent context-free grammar. Thus, a language is context-free if and only if some PDA recognizes it. Cool. So we've shown that this class of context-free languages is not just the class generated by context-free grammars, it's also the class captured by pushdown automata. These things have some kind of equality. And good for you guys on sticking through one of our probably top 3 tricky proofs of the course. That's a big back and forth. Both those constructions are hard, just like our proof involving the GNFA was hard. Now, the last thing I want to talk about today, now that we've shown 2 equivalent mechanisms for recognizing or generating context-free languages, is things that are not context-free. So languages that are not context-free. Of course, we certainly haven't ruled this possibility out. We've seen lots of non-regular languages that are context-free, that can be recognized by a pushdown automaton or a context-free grammar. But it turns out there's some languages that are not context-free. There's a world beyond. And yes, there is a pumping lemma. So we'll show this proof, and if anything, or at least we'll sketch the proof, we'll show the intuition behind it. And if anything, I think this intuition should make the first one a little bit clearer, because it'll show you how these 2 pumping lemmas have some fundamental ideas in common. The idea behind the pumping lemma for non-context-free languages will be the same as before. That is, we'll show that all context-free languages have a certain property, namely, sufficiently long strings can be pumped. And then to show that a language is not context-free, assume it satisfies what we'll call the context-free pumping lemma, or CFPL, and find a contradiction. So when we're finding this contradiction, we'll show that the language can't be pumped by finding some string that's in the language and long enough for which no pumping is possible. Again, pumping will mean dividing it into strings and showing that it satisfies certain conditions. And I think we're probably ready to just see the theorem. And the theorem will go as follows. So if L is a context-free language, there exists a pumping length P such that for all sufficiently long strings in the language, so for all strings S in our language such that S is at least as long as the pumping length, S can be divided into 5 substrings. S equals U, V, X, Y, Z, such that, so again, we're just dividing it into a bunch of substrings. Yes, there are 5 of them, but there are 5 of them that perform pretty much the same roles as our original 3. So the conditions are, for each I greater than or equal to 0, the string u, v repeated I times, x, y repeated I times, z is in the language. So that's our first condition. It's telling us that instead of repeating one string y, we'll repeat both v and y. The second condition is that vy, that is, the strings to be pumped, are non-zero. So this is like the condition y greater than 0 that we had previously. And condition 3, vxy is at most the pumping length. And this is just like our condition that xy had length at most p before. So with the exception of splitting into 5 substrings, this should look very similar to the pumping lemma for regular languages. It's telling us that if L is context-free, then there's some length such that sufficiently long strings in the language can be pumped. Pumping looks similar. We have 3 conditions again. One condition says that the string that can be pumped, the substrings v and y, are not 0. Another one says that a certain substring is not too long. And the third one, or the one I've listed as number 1 here, the pumping condition, says we can repeat these substrings any number of times, repeat v and y some equal number of times, and we get a new string that's in the language. The idea behind this theorem is that we can find loopiness in context-free languages the same way we could find loopiness in regular languages. So context-free languages have context-free grammars with a finite number of variables by definition. Give me a CFL. I know it has some finite context-free grammar. Any sufficiently long string have derivations that always use some variable twice. So again, the logic is kind of simple. It's intuitive. If we have some really, really long string in our language, all the ways to derive it must have a lot of steps. Every step replaces some variable, and there's a finite number of variables. So really, really long strings mean really, really long derivations, mean we're going to use some variable in our CFG at least twice. If we repeat a variable, this creates a loop we can pump. So the idea is something like if we have a derivation that looks like a to 0a1 to 0, 1, for example. In this particular example, I use the variable a twice. So instead of using the second rule that looks like it replaces a with the empty string, I could repeat this rule an arbitrary number of times. Well, so my first rule is still the same. In other words, I can conceptualize using this variable twice as going around a loop that I can do as many times as I want and still get a string in the language. And these string 0, 1s that have been created can be pumped, right? See them again? That means I can generate them by going around this loop multiple times. So that is our intuition here. And that's the idea behind the proof that we will proceed to quickly sketch out. So here's the proof of the pumping lemma for context-free languages. So let's let G be a context-free grammar for a context-free language A. And let's let B be the maximum number of symbols on the right-hand side of a rule. So in other words, if we have some variable and we're drawing a little parse tree for it, and there's a bunch of symbols that it creates, there's at most B of them. Thus, any parse tree has at most B nodes at level 1, right? Because I've said by assumption, I replace any variable with at most B symbols. At most B squared at level 2. That's because I had B nodes at level 1. I replaced each of them with at most B more nodes. So at most I can have B squared nodes once I've gone down 2 levels in my parse tree. B to the H nodes at level H. This is just by the same logic. And so on. So what we're doing here is we're bounding the number of nodes in our parse tree to try to find a place where we know a derivation has to repeat. So set our pumping length to be P equals B to the V plus first power, where V is just the number of variables, the size of the set. So now, the convenient thing about this particular pumping length is that any string S in our language of length at least P must have a parse tree, or all of its parse trees, if it's ambiguous, with height at least V plus 1. So what I'm saying here is, now suppose I've got a long string in my language. The length is at least P, so it's B to the V plus 1 symbols. We already got a bound on how many symbols we can produce in a finite number of rules, looking at our parse tree. So this is true. Any way of deriving this string must come from a parse tree with height at least V plus 1. And this is because parse trees with height at most V have at most B to the V leaves, nodes. All right. So now we've said, we've been able to say that any really long string has to have only big parse trees. So let's let tau, this is a Greek letter tau, it looks like a T with a curly top, be some parse tree for our string S. Because tau has height at least v plus 1, there is some path of length v plus 1 with v plus 2 variables on it. So the logic here is just as follows. Sorry, not v plus 2 variables, v plus 2 nodes. Right? Any path with v plus 1 edges has v plus 2 nodes. Thus, some variable appears twice. So if I draw some picture of tau over here, starting at my start variable, which has a lot of children, later on in the tree, maybe I see this variable r. Later on in the parse tree, I see the variable r again. The claim is just, there's some path in this parse tree that has length v plus 1, because that's the height of the parse tree. It has v plus 2 nodes, of which v plus 1 are variables, and that's more than the number of variables. So by the pigeonhole principle, we've got to see some variable twice. So we'll call this variable r, and we'll let r be the first variable that repeats as we go from the bottom up. So I'll look at my long path in tau, I'll start at some node, I'll go up, I'll keep track of all the variables I see. Eventually, because I'll see at least v plus 1 variable, some variable must repeat, and we'll call that first repeating variable r. This looks a lot like our repeating state in our pumping lemma proof. So finally, now we divide S, not capital S, little s, into substrings u, v, w, x, y, not w, and one too many, u, v, x, y, and z, according to this picture. So in particular, I'll say, look at all the nodes that descend from my final variable r, all the terminal symbols, and we'll call that string x. All the ones that descend from my second occurrence of r, but not my first occurrence, I'll call these v. I'll call these ones over here y. And all the nodes that descend from my start symbol, but not from a variable r, I'll call this string u and this string z. So now I've taken the string that's ultimately derived, this string of terminals, and I've divided it into u, v, x, y, and z. So now I claim our 3 PL conditions hold. I'll start with the easy one. So claim 2 says that the length of v plus the length of y is greater than 0. And I claim this holds because we can assume, without loss of generality, that tau is the shortest parse tree for S, and thus some symbol descends from the top R, but not the lower R. So the logic here is just that if there were no terminal symbols that descended from our top R, but not from our bottom R, then we would just have a straight derivation of variables from R to R. And we could simplify the parse tree by eliminating the first R and just replacing it with the second one. So without loss of generality, we know that there are some symbols in V and Y. Our third condition says Bxy is at most P. And this follows because we find a repeated variable R in the bottom B+1 levels by definition, or because there are only V variables. Thus, the height of the big tree rooted at R is at most V+1, and it has at most P equals V+1 leaves. So the logic here is just if we consider this big tree descending from the top R, because we've looked for our first repeating variable, we know that we found a repeating variable in the first V+1 levels. In other words, the height of this tree descending from R is at most V+1, which means that there are at most B to the V+1. Sorry, I didn't mean to write V+1. I meant to write B to the V+1 leaves. This is by assumption that B was a bound on our branching factor. Finally, our first condition, the last thing we have to show, is that U, VI, X, YI, Z is in the language. What did we call our language? We called our language A. So U, V to the I, X, Y to the I, Z is in the language for all I greater than or equal to 0. Why? Well, if I equals 0, see the parse tree that starts at our start symbol
and looks exactly like the parse tree we just saw for S, except when we see our first symbol R, we replace it with the parse tree that descends from our second symbol R in the parse tree for S. So we know this parse tree, whatever it looks like, creates a string X that's a valid derivation from R and grounds out in all terminals. So we can just plug it in right here. And we know this parse tree is valid. And it's a parse tree for UXC. Now, if I equals 2, this is the parse tree for U, V2, XY2, Z. We're going to draw a parse tree that starts with S, that looks just like our parse tree above. It descends to R, and then instead of finishing off our parse tree, as in this picture, with the small tree, we'll replace it with the big tree that descends from the first R. So we'll have X at the bottom, and then we'll have V and Y. So the end of our parse tree looks like the parse tree descending from the big R, the first R, in our original parse tree. And then we'll build S and our first R as before. So we end up with a parse tree for UVV XYYZ. And of course, we can do this repetition to create a parse tree for U, VI, X, Y, I, Z, and all I greater than or equal to 0. So this completes our proof. It's a lot of writing, but remember that essentially what we did was we said, well, let's bound the branching factor, the number of symbols that descend from any variable, and we'll use that to say that any sufficiently long string has to repeat a variable. If we repeat a variable, then we can build new parse trees by repeating that variable fewer times or more times. And those new parse trees derive the strings u, v to the I, x, y to the I, z for any I greater than or equal to 0. So that is a property that all context-free languages have. And that's the property stated in the context-free pumping lemma. So at this point, I think we are over time, so we'll do examples for the context-free pumping lemma next time. So that will wrap us up for today. Next time, we will see Turing machines, which are arguably our coolest and best automata, greatest automata of all time, the champions. Let's see. Recall, we have homework 4 due Monday at 11:59 p.m. Eastern Time. That is Monday, 7/26, I believe. And the reading for this section, in case you'd like to see the proofs that we did in some detail, in more detail, flesh out the bits and pieces, it's CIPSR 2.2 for the proof that context-free grammars are equivalent to pushdown automata, and CIPSR 2.3 for the context-free pumping lemma. So thanks very much for watching. Have a great weekend. See you next time. Bye.